Hello everyone, welcome to this video. In this video, we will build a three-phase circuit. So first, whenever the tab is at home, so this will be the page of the MATLAB whenever you open it. So here is the current folder window, this is the details window, this is the editor window, and this is the command window, and this is the workspace window. So what we need to do is to create a model, Simulink model. So you need to find the Simulink button or icon and to click on it. Once you click this, you will have this window and we need to create a blank model. So we click a blank model and this will be our model. Let's maximize this screen and start building this circuit. Again, we need to build a three-phase system. So we need to have voltage sources, AC voltage sources. So again, you can go through the library, look for Simulink. So we are looking for Simulink. Here it is Simulink, double click, look for electrical, double click, and then look for specialized power systems, double click, and then you look for sources, double click. And here is the AC voltage source. As you see, we have different sources here. We are interested in this one. So I will drag it and have it in my system. So I want to build a three-phase system. So let me first rotate it in a clockwise direction. So I want to rotate it in a clockwise direction to have it in an horizontal way. Okay, so this is my first voltage source. Now let me set the values. So I want for the peak amplitude to be 10 volts. The phase angle is 0 for phase A. The frequency, I want it to be 50 hertz. Then I do apply and okay. And for the this voltage source, I want now to copy it and to have another two of them. Okay, so these are my voltage sources. So this is here, and let me have this one is here. So now I want to modify. So for the same peak amplitude, so the phase angle of the of phase B, it will be negative 120. Same frequency, of course, and apply OK. For the third one, which is the phase C, we need to, for the phase angle to be 120, positive 120, same frequency, apply OK. So now I have the three voltage sources, and now I want to connect them in Y. I want to connect them in Y, and after connecting them in Y, I want to ground them. So I'm looking for a ground. So I'm typing ground, and this is my ground here. I will bring the ground closer to the neutral point, and I will connect the ground to the neutral point. Now the three voltage sources are set. They have the same magnitude, and they are shifted by 120 degrees from each other. So for phase A, we have the phase angle 0. For phase B, the phase angle is negative 120. For phase C, the phase angle is 120. Now we need to have measurement blocks. So I will type the first letters of the word measurement, and then I'm looking for the three-phase VI measurement. So I need to have this one. And I want also a current measurement, just one current measurement. So I'm typing again measurement. So this is the current measurement. I need also voltage measurement. So I'm typing again the first letters of the word measurement. And here is the voltage measurement. And I need to have also power measurement. So I'm typing the first words of measurement. So here is the power measurement. And this power measurement is a single phase power measurement. So I need to have another one, which is a three-phase power measurement. So I'm typing again the first words of the measurement, and I'm looking now for power measurement three-phase. As you see, power measurement three-phase. So this is the same as you see, same block, but we have here in parentheses the three phase. Now I can connect all this stuff. So I want to connect the current measurement in one phase only, and then we'll measure the line current in phase A. The other currents will have the same value but shifted by 120 degrees. And then I will use this block in order to have the three phase variables, currents and voltages. So I connect phase B with phase B, I connect phase A with phase A, and I connect phase C with phase C, like this. So you can also make it symmetry like this. Okay, now I need to have a load. So I will look for the series RLC branch, but this time I will look for the three-phase series RLC branch. Here it is, three-phase series RLC branch. And then I will connect this branch with the source through the volt ampere measurement block. As you see, I'm connecting A to A, B to B, and C to C. And of course, the circuit is still open, so I need to connect them in Y. So I'm connecting the other terminals together in Y with a neutral point. And again, I need to have a ground here at the other side. So I'm typing here ground. Here is my ground. And then I can connect this ground to the neutral point. Okay. Now I have the circuit almost done, but I need to connect the measuring devices and the displays in order to see what variables we have. Okay, so let's start with the voltage measurement. So the voltage measurement, we need to measure two voltages. One voltage is the line to neutral or phase to neutral or line to ground or phase to ground. All these names represent one voltage. So the positive terminal will be connected to one of the lines. It could be phase A, B, or C. And the other terminal should be connected to the neutral point. But since the neutral point is grounded, so I can connect it to the ground. So let me copy and paste this ground component, this ground element, and I will connect now the other side of the voltage source with the ground. Since we are dealing with AC components, so I need to have the RMS blocks. So I will type RMS, and here is my RMS block. So I will connect the RMS block with the voltage measurement and make sure that here the frequency is 50 Hertz. Since the source frequency is 50 Hertz, apply and OK. In order to see this voltage, of course, I need a display. So I'm typing a few letters from the word display, and here is the display. So this display will show me the voltage, which is phase A to neutral, phase A to neutral voltage, and this voltage is measured in volts. And of course, this is the RMS value since it is connected after the RMS block. Same structure should be done for the current, for the line current. So let me copy and paste all these three blocks. So I will copy, do paste somewhere here, and bring it using the arrows or using the mouse. Okay, so I'm bringing it here. Now I'm connecting the current to the current measurement to the RMS block, and I'm changing this now name to be I in line A or in phase A, and this will be measured in amperes, of course. So here I have the line current measured as well. So in order to measure the power in this phase, I need to have a power measurement component here. So let me have this power measurement component. Let me do the following. Let me have this power measurement component here. And now I want to connect the voltage input to the voltage input. And here is the voltage input. And now I want to connect the current input to the current input. And you need to make sure that you are connecting the voltage and the current before the RMS block. And of course, I need to have some displays in order to show the active power and the reactive power as well, So I'm copying and pasting all these displays. And now I want to change the names here. So this will be P for one phase. So I will write one like this, one phase. And this P1 phase will be measured in watts. And this one will be a Q. So this one will be Q1 phase measured in volt ampere reactive. So this Q, and I will type here one phase, and the unit of measurement is volt ampere reactive, Okay, so now I want to measure the entire three-phase power. So now before that, let me make sure that we have the same frequency as the source frequency, and keep only the fundamental harmonic here, which is number 1, and apply and OK. So in order to measure the three-phase power, the power in all three phases, so I need to have the three-phase voltage connected here from the three-phase measurement device, and the current as well. So, and before that, I need to make sure that we are taking the appropriate voltage. So you double click on this three-phase volt ampere measurement. You choose phase to ground and you choose yes. So they are set already by default. So I don't need to change anything. So here I need to make sure that I have the same frequency as the frequency of the source, and to keep only the first harmonic, since the first fundamental component, since I'm not interested in calculating any harmonics in this model. So apply and OK. And again, I need to have one display to show the values of this three-phase power. So this is the display, and the other display to show the values of the three-phase reactive power. So copy and paste, and then you connect them to the reactive power. So now I want to change just here to make it three-phase. So we understand that this is the three-phase reading. And here I want to change the reactive power also to be three-phase, and it will be measured in volt ampere reactive. So again, we need to have a power GUI, because this component is very important to have, and actually we will not be able to run the system without having it. So you need to make sure that you have it all the time. For the stop time, we make it 0.02, which is 20 milliseconds, which is one period if the frequency is 50 hertz. So when you divide 1 over 50, it will give you 0.02, which means that this is the period time. Okay, so I think so far I have almost everything. So I need to have a scope in order to see the variables. For the scope, I need to have two inputs. So either you do right click and you do signals and ports. You select the number of ports from this point, or you click on the scope and you go to a file, and here you will see number of ports, and then you select the number of ports. So here we have two ports, and one of them should be the voltage and the other one should be the current. So I can see now on the scope the three-phase voltages and the three-phase currents. Now let's set the values for the three-phase RLC branch. I will start with having only resistance, and I will have the value of 3 ohms in this model. So I do apply, I do OK. So I believe that this is the entire circuit. So let me run the circuit and see whether it is correct or not. Okay. So what we see that the value of the active power here in one phase, measured in one phase, is 16.67 watts. And for 3 phases, it's 50, and it's actually this number multiplied by 3, because the power is the same power will be consumed in the 3 phases. So the 3-phase power is the single phase power multiplied by 3, and this is a good result. We see that the reactive power is equal to 0, because as you see, it's times 10 to the power of negative 15, and here it is the same. So let me change the format for writing. I will use the bank format, which is for money, but I like this format because it has only 2 digits after the decimal point. So let me do it for this. Then we will have the result nicer, let's say. So we see that the reactive power is equal to 0 here and here, because we have a pure resistive circuit, So this is the active or average power in a single phase. This is the reactive power in a single phase. This is in a 3-phase. This is also the reactive power in a 3-phase. This is the voltage, line to neutral voltage, Actually, I need to measure also the line to line voltage. So let's have another voltmeter here. So I will select another voltmeter. So I need to copy this and to paste it somewhere. Let me paste it here. So I will have this voltmeter here, and this voltmeter, in this voltmeter, I want to measure the line to line voltage, and I will measure the voltage between phases A and B. So as you see, I connected it between phases A and B. And of course, I need to have an RMS block in order to find the RMS value. So let me copy all this stuff and paste it here, and I will connect it to the voltage measurement block. So I'm connecting to the voltage measurement block. So, and this voltage now will be VAB, and this VAB will be measured, of course, in volts. So let me run the circuit once again. And what we see that the VAN, the voltage between this point and the neutral point or the ground, is equal to 7.071, which is 10, the amplitude divided by square root of 2. And we see that this value is 12.25, which is 7.071 multiplied by square root of 3. So if I'm using my calculator right now, and let me double check this value. So I'm multiplying 7.071 times square root of 3, and the result is 12.247, which is 12.25 volts. So as you see that this voltage is the same as the line to neutral or phase to neutral or line to ground or phase to ground voltage multiplied by square root of 3. And of course, it should be shifted by 30 degrees. Let's see what we have here on the scope. So I will double click, and we see that we have 6 signals. 3 of them are the voltages, and 3 of them are the currents. Since here, as you see, we have 3 voltages, VAPC, and here we have 3 currents, IAPC. And of course, we can, in the view, have the legend here. So we see that we have 3 voltages, 3 currents. And of course, we can also, in a view, go to configuration properties. We can go to time, add the time label, apply. So we see that here we have this time written here. We go to display, and we can also add the Y label, and the Y label will be, let's say, voltage, let's say voltage in volts, of course, and currents in ampere. So, and current in all these phases. Okay, just this is just to demonstrate, as you see here, voltage and current. So I will do okay. And as you see, if I switch off the 3-phase currents, so I see here the voltages. I see the voltages. And as you see here, we have a 3-phase voltage. So this is the phase A is actually this one, the yellow one, because it starts from 0. Phase B is this one. And phase C, actually, phase C is the red one, and phase B is the blue one. Why is that? Because as you know, that phase A has a phase angle of 0, so it starts from 0. Phase B has a phase angle of -120, so it lags phase A by 120 degrees. And we see that the blue sine wave lags the yellow one. And here, phase C has a phase angle of +120, which means that phase C leads phase A, or phase A lags phase C by 120 degrees. And of course, at any instant of time, the sum of these 3 voltages will be equal to 0. So if I go to tools, and I go to measurements, and then I will go to cursor measurements. So I will have here these cursor values. So let me make it the screen a little bit bigger. And as you see here, for example, when for scale 1 here, we see that voltage, this yellow dot, which is the voltage in phase A, this yellow dot, is equal to 9.985, which is actually 10, because the amplitude, the peak value in the source as we had is 10, okay? And we see if this value for the blue and the red one, if I switch to any of them, the blue or the red one, so we see now the dot is in the blue, we see that the value is -5. So here we have +10, here we have -5 for the blue, and it will be the same for the phase C, which is the red one. So as you see here, we have a red dot, so it is again -5. So -5 plus -5, it will be -10, plus +10, it will be 0. And wherever you go with this cursor, you will see that their sum is equal to 0. And this is the beauty of the 3-phase. This is why they are apart by 120 degrees. So all the time, the sum of the voltages or the sum of the currents will be equal to 0. And since the sum of the 3-phase currents, let me have them here back and remove the voltages. So, and because the sum of the 3-phase currents in any point is equal to 0, this is why we can remove the neutral connection or the 4th wire from the 3-phase system and save one additional wire. So this is the point behind having these phases shifted by 120 degrees. So now what we can do is to manipulate this load. So we can, for example, switch it to RL component and have L is equal to 0.001. So I don't want to change the value of L. I will do apply, I will do OK, and then I will run the circuit again. So what we see that now we have reactive power because we have L component. We see that this reactive power is 1.73 in one phase, and in three phases will be the same value multiplied by 3. So if you multiply it by 3, it will be 5.18. The voltage is the same, both the phase to neutral voltage or line to line voltage or phase to phase voltage. They are the same as in the previous case, but the current, of course, is different because we have different current. Since different impedance, since the current is different, also the power, the active power will be different. But of course, this active power in single phase will be 1/3 of the power in three phases. Again, we can also make it RC, and let's make it 1 times 10 to the power of -3. I will do apply, I will do OK, and then I will run the circuit once again. What I see that I have a negative reactive power. And if you multiply this negative reactive power by 3, you will have the three-phase power. So as you see, the capacitor usually gives the system reactive power, and this is why we are using capacitor banks in the distribution systems in order to enhance the voltage profile and to provide the load with a reactive power instead of drawing the reactive power over the entire transmission line. And of course, we can have it RLC, so you can have it all the three parameters as it is shown here. I will do apply. Okay, now we have RLC, and if you run it again, we will see that we have these values. So you see that the reactive power is still negative, which means the capacitor here is dominant. So the circuit is still a capacitive circuit. And if I look to the scope at this time, let me keep only phase A voltage and phase A current. So I see that the peak of the current occurs before the peak of the voltage, which means that we have a leading current, So this confirms that the current is leading, and thus the circuit is capacitive, has a capacitive character, and the reactive power is negative. If we switch back to the RL circuit in order to show you the relationship between the voltage and the current, so I will do apply, OK, and run the circuit once again. We see that the reactive power now is positive because the inductor will have a positive reactive power. If I look to the scope, I see that the peak of the current comes after the peak of the voltage, which means that the current is lagging. We see that it lags by a small angle because the value of the inductor here is small. So if I increase the inductance here, for example, let's say that it will be 10 times 10 times 10 to the power of -2. So let me see what the change will be in this case. So if I look to the scope, I see that the current is lagging, and now it lags by a bigger angle. Because I increased the inductance value. So you can change the values as you want in order to see the response. Of course, in each time or with each values, you can have the active power in one phase, the reactive power in one phase. If you take the square root of the active power square plus the reactive power square, this will be the apparent power. If you divide the active power by the apparent power, it will be the power factor. This is the line to neutral or phase to neutral or line to ground or phase to ground voltage, RMS voltage. This is the line current. In phase A. And here is the line-to-line or phase-to-phase voltage. So this is about the Y circuit, since the sources are connected in Y, and we see that the load is connected in Y as well.